All right, so let's get started on how you work this kind of problem where you have known starting amounts and you have K. As you start this process, you see here in red the things that you know. And down below, I'm going to start with the idea that X, the amount of nitrogen, is the thing that I don't know. I give it the simple variable name here, and we'll see why in just a moment. It's because it turns out that stoichiometrically, the amount of nitrogen at equilibrium is related to the other materials that exist in the container. And we see this in the next part of the Rice expression. This is such a key thing to understand, this particular part of the table. This is the central feature in how I use algebra and stoichiometry together to be able to basically populate the table, not with a whole bunch of different numbers that I don't know, but only one number that I don't know. Because I've decided I want to know X, what can I learn? Well, I'm going to populate the rest of the table with how X for nitrogen relates to everything else. If I started with 0 and I ended up with X, then the change had to be plus X. That seems apparent. And now I have a stoichiometric relationship for the amount of the other compounds. If I have X nitrogen, then I must have 3X hydrogen. And so I have X and 3X for the amount of hydrogen and the amount of nitrogen. Notice these are positive values here because I'm going from 0 to 3X or 0 to X, which means this reaction is going to, must have been formed to go in the reverse direction. And we see that that must be true. If I had no hydrogen or nitrogen, it had to have been gained from somewhere. What's the amount of ammonia that I have gained or lost? Well, stoichiometrically, it must be 2X. That's X, that's 3X, that must be 2X because of the stoichiometry. But it must be going away. Why is it going away? Because these guys are forming. It's always the case that if I have a Q versus K reaction, then the stuff on the left gets small and the stuff on the right gets large. If I have a Q greater than K reaction, then the stuff on the right gets small and the stuff on the left grows. In this particular case, I must have a Q is greater than K because this stuff has to decrease to get to where K is, whereas these increase. Well, now that I know this value and this value, I can compare them to the initial concentrations and find out my final equilibrium amounts, all in terms of X. So I started with 0 and added 3X. 3X must be the amount at equilibrium. I started at 0 and added X. I must have X at equilibrium. I started with 0.1 and I lost 2X. Then at equilibrium, I must have 0.1 minus 2X. Look what I've done here. I have completely rewritten this problem, which started out as a bunch of unknowns, as one unknown, X. Now that I know this information, I am very close to solving the problem, because remember, what I got in my back pocket is the thermodynamic constant that I was given from the back of a book somewhere.